Good morning, everyone. Welcome back to this workshop on P4 programmable switches. We are starting our day number 2. And to start with, I want to review what we did yesterday. We cover lab 1 and 3, the basic of P4, or even the pre P4, I would say. We learn how to use the tool, the compiler, write simple code. We compile, and when we run the code in the data plane. I will be posting the videos, so I still don't have access to this. I think I have a message from the moderator, the organizers, Laura, and she mentioned that the video will be inside the workshop room in the venue. So the way that you access the workshop, there seems to be, I have a different view, I just access using Zoom, but if you go through the platform, you will be able to find the videos in the workshop room. Also, when I have access to them, I will be posting the videos in our website, the workshop website. So that's the plan regarding the videos. Day number 1, again, we covered all these topics. Lab 1 and 3, lab 2, we didn't have time during the morning, but in the afternoon, we completed that, and the video will be available. So all that will be posted. There are a few messages here. Isvan, hi, I ran into some issues doing the labs, doing lab 3, was not able to get the mouse cursor inside VM. What is the key combination to that? So Jose, you wanna address that observation?
Yes, hello, Ispan. Yeah, as I mentioned, that could happen. It's rare, but you might wanna undock your VM and then dock it again and see if that solves the problem. That issue could happen. So
okay, thank you. Can you hear me?
Yes, I can hear you.
Yes, so usually in a virtual machine, there's a write control or other key combination, and I was thinking that maybe there is a combination, a key combination that can be done to do that, but I will try the docking. Also, I had another problem. I was doing a lab 2, and by mistake, I closed the diagram. So, okay, no problem. I said, I will start over. So I open lab 2, I open the diagram, I hit run, and after that, I was not able to get a terminal. So holding the right mouse key on the H1 or switch 1, it should give me the drop-down menu, the terminal, but I was not able to get that. How, what is the workaround? What I did wrong?
Understood, yes. That could happen because you didn't really stop the emulation. What I suggest is running on the mininet terminal. You run the command exit, and that will kill all the mininet instances. Another option is opening a Linux terminal and running the command that I type in the chat, and that will clear your mininet the mininet topology that you just opened.
Oh, okay, thank you. That's cool. Thank you. Very good labs. Thank you, guys.
Not a problem. Let us know if you have any other issues.
Okay, thank you.
Thank you, Juan. And perhaps Jose, is a good idea to show this before we start. We will continue, but before we start the first lap of today, just quickly how to clean when there is a problem.
Yes.
You wanna shut down everything and then open again. So just to show how to clean everything before opening again a scenario. So that's a good good observation. Should you have your hand up? Feel free to unmute yourself.
Hi, good morning. Yes, I didn't run into problems when doing the labs. However, the last step in lab 3 says check if the host 2 receives the packet, the message that's sent by host 1. I can see the switch, the programmable switch received the frame in the middle, but I don't see anything popped up on host 2, even though we run the script for receiving .py. So I wonder, I don't see anything pop up on host 2 for the last step. Is that normal?
Yeah, I don't know if you, Jose or Eli, want to address that, but if I understand well, is should you are not seeing the message at the receiver side. That's what you are indicating.
That's right. They type the hello world, but and we run a script on host 2 trying to sniffing on the receiving, I suppose, but I don't see anything popping up on the host 2 terminal.
You want to go ahead, Jose, or
just go ahead, Lee.
All right. I mean, there are a few things that you can do to troubleshoot. I would say the first thing is just look at the logs on the switch. So when you remember yesterday when we typed nano message, it will show you the logs that are happening. And there you should be able to trace if the packet is being sent out of the switch or if it is just being dropped there. So that's the first thing you can do. And then also for further like troubleshooting, you can try to run like TCP dump or Wireshark on the receiver, and you will see if any packet is being received at all. Now, just like an observation that the scripts that are sent and received, those are like customized in a way that they expect the packet to be received in a certain ways. But sometimes, let's say you write your own P4 program, you did some changes, and then the receive won't be able to display that packet, although the packet might be received on the receiver. So I would say first start with just looking at the logs and make sure that the packet is sent out of the switch. If that's the case, then run TCP dump and see if it's being received on the H2 receiver.
Or Wireshark, right, Eli? Wireshark, which is simpler than TCP dump.
Yeah, or Wireshark for like a graphical interface. But yeah, I mean, these are some very common things that you have to try to do them as you write your P4 program for troubleshooting purposes. I don't think there's like a specific, error or problem that caused this to happen.
And we can do it as an example today, the Wireshark, because all the tools that are available in a Linux machine, I mean, we can use any. This is just a regular package. You just craft it on your own way.
Exactly. Yeah, for sure.
Okay, these are good observations. So back to our program for today. The plan for today is to talk about parsers and match action tables. So these are key elements in the programmable data planes. So briefly before we do that, I want to share this screen. This is from yesterday. And again, we are always working in the data plane. So here is a line, control plane up, data plane down. And here is where we are. So packets enter, packets exit. So what we're going to be doing today is the parser, basically the unit that will parse the headers, header fields, and then match action tables. Thing is for today. So tables are very important because we want to match against an entry in a table, for example, routing table, we're trying to match the incoming destination IP address with the entries, one entry in the routing table. So that's what we're going to be discussing today. Back to our website. So match action tables, parsers, and then we will have one lab for parser. We will write code to do a parser. I think it's IPv4 and IPv6 and Ethernet. We will have to parse those headers. And then we will have, if the time permits, match action tables, 2 labs, or at least 1, I would say. Hopefully we will be able to do 2. And that'll be all for today. During the afternoon, what we do is office hour. Just any question you have, or if you want to work on a lab, that's what we did yesterday. So we will do that again today if there are any suggestions. So let's start. And by the way, I would ask, the slides are already online. So I will just go over these slides, parser, match action tables, explain what are those, and then we will start the labs. And before I have here some questions. Hussein, I have a general question. I'm on the east side of the country, I would say, Eastern time, and my schedule partially doesn't match the program. Will the recording be available? Yes, Hussein, we will be posting the recording as soon as possible. Hopefully today we will have the recording for yesterday and tomorrow morning for today, and so on. Okay, so let's start with these 2 topics, units of the data plane that are key, parser and match action table. So we'll start with the parser. And before we start, I want to, my co-organizer is here. Marian, are you here?
Yes, I'm here for you.
Good morning. And at any time, feel free to jump if I miss something or you want to add something as
Sure.
we do the presentation.
Sure. I'm good. Thank you.
Okay, so the parser is this first unit. The packets are arriving to the data plane from the left, and they leave the data plane from the right through an egress interface. So the first thing that we want to do is to parse the packets. So these are raw bits that are coming from the left, and we want to parse. So in order to do that, we will create a finite state machine. So the state machine follows the order of the headers. For example, we will want to first parse the layer 2 protocol header, Ethernet, example Ethernet. Ethernet encapsulates IP packets. After we parse the Ethernet, we will parse the IP version 4, or could be IP version 6, or ARP. After that, the upper layer transport and so on. Whatever we want to parse, we have to describe in the parser. So it's useful to keep in mind the header and the header fields. So here we have an example. This is an IP version 4. On the left side, we have an IP header. The fields: version, IP header length, total length, source IP, destination IP, and so on. The way to describe that in in P4 is we define our IP version 4 type. This is just a name, and then all the different fields according to the standard. If we want to define our own protocol with our own header field, we can do so. It's just similar to what we have in this example. So in this example, we have a field of 4 bits, which is the version, which is matching this diagram here. For example, source IP address is 32 bits. This is just a type def, equivalent to 32 bits. And destination IP address the same. So that's important to remember. So about the parser. So how does a parser look like? On the left, we have a diagram. On the right, we have the real code of a simple parser. First observation, the parser has at least 3 states. There are 3 predefined states: start, accept, and reject. So the parsing process always starts in the start state. So that's why we have here start, and then there is an arrow. That means we are transitioning to another state. So any other states other than these 3 states can be defined by the programmer, by us. So this is the state machine. The first state here is where we will start. Notice that the P4, and I'm using P416. This is the way that we indicate that we're using P416. And just a refresher, there are 2, let me say, version of P4. One is P414. This is the older that was started in 2014. And then the P416 that is started in 2016. So P416 is the current version of the P4 language, and we're using P416. So P416 has a transition statement. So if I want to go from a start to parse Ethernet, I will use this transition statement and then the name of the next state. So parse Ethernet, so transition parse Ethernet. What is going to happen next is we will enter the parse Ethernet state. So in the parse Ethernet, the first thing that we see here is packet.extract. So the extract is a method that can be used to fill in the fields of the, in this case, Ethernet fields. And one thing that I didn't say before is that packet, right here, packet is an input parameter. And header, HDR, is an output parameter. So we're filling this header structure with the raw bits that are received from the packet. So packets are the raw packet, and header will have all the fields of all the different headers. So how do I extract? I just call this method packet.extract. Then we have again a transition, but this time we have a transition with a select statement. And the idea here is that we can branch to multiple potential states. In our diagram, we have just a branch of two possibilities here. Parse IPv4, that's the only type of network layer protocol that we will parse. If we don't receive IPv4, we will just reject. That means that's an error. We cannot, at least our data plane will not be able to parse any other network layer protocol. So the reject, a little bit about this reject state. I was looking a little bit more information. The P4 specification seems to be silent. So that means it doesn't say what to do when a packet reaches the reject state. So I would suspect when I was preparing this slide, I was suspecting the packet would be dropped, and apparently that's what happened. But the specification doesn't say that. So it seems that it's left to the architect. For example, if Tofino, if Intel is implementing its hardware, it's up to them what to do when the packet reaches the reject state. So that's something about the reject. About the accept, so a packet reaching the accept state is further processed by other P4 programmable blocks. That means it's gonna move on with the ingress pipeline. That's the basics of the parser. I don't think there is any other secret. It's just a transitioning from one state to another. What we're going to be doing in the lab is parsing Ethernet IP version 4 and IP version 6 packets, and that's why we put the headers in this slide. The topology for lab number 4 is going to be simple, similar to the topology that we had yesterday, just two hosts, H1 and H2, a switch 1, which is programmable, IP address 10.0.0.1 and 10.0.0.2, MAC address is given also here, so we can easily recognize the MAC address. So hopefully, by the end of this lab, we will be able to define headers, not only for Ethernet IP version 4 and IP version 6. One of the key advantages of programmable data plane is that we can come up with our own header fields or headers or protocols. It's pretty easy. Then we will implement a parser and then test and verify the switch behavior. So those are the goal of lab number 4. That's the first topic that we will be discussing today. The second topic is match action tables. And by the way, Eli, Jose, and Ali, again, I want to give credit to the grad students. They are the ones who work really hard for this lab. Feel free to jump at any time if I'm missing something that is important and relevant for the lab. So regarding match action tables, so they are the fundamental unit of the match action pipeline, the processing, what is happening in the switch. So in the V1 model, notice that after the parser in the header, we have all the header fields already populated, and we can do some processing. The match, trying to match against entries, for example, routing table, just a match action table. And in the egress pipeline, we have again the same arrangement. So we can use to implement traditional routing tables or switching table. That means if we want to match against MAC addresses, we can do so, or against IP addresses, or we want to implement access control lists. Those are the traditional ways to use tables, but are not the only one. For example, we can use tuples rather than just individual header fields. So that's why it says here they can implement custom user-defined complex logic. So what is in a match action table? The table specifies what data to match on. I'm giving this simple example because we're familiar with it. We want to match again the incoming destination IP address. We specify a list of possible actions. Example, one action would be forward the packet if there is a match. Forward the packet to egress interface 2 or 3. Those are actions. Specify a number of optional table properties. So we can define what is the size of our table. If we want to have a default action, if there is not a hit in the table. That means there is no matching, so we can set a default action, and we can also set static entries. So what is in an entry? So the table is just a set of entries, right, and several columns, or several entries, and there will be 3 columns. One column, first column, will be a specific key to match on. That will be, again, the same example, destination IP address. An action that is executed when a packet matches the entry. As I said before, we will forward the packet. That's the action. And the action data. So action data is what is the data that we need to forward the packet. For example, egress port 3, the packet should go to egress port 3. That will be the action data. Another action data could be the MAC address to use for the next hop, because MAC addresses are changed in every hop between routers. This is another way to visualize the match action table. Again, there are several entries, 3 rows, 3 entries in this case, and it could be many more, 1,024 or millions of entries, million of rows, and there will be 3 columns. Again, the key, the action, and the action data. Notice that we could have here a line, because the table is in the data plane, and this table is populated from the control plane. So the table is not populated from the data plane, it must come from the control plane. For example, when you install a static route with Cisco IOS, IP space route, IP address, subnet mask, and then basically you are in the control plane, and then that will be pushed down to the data plane. So that is the analogy with the traditional devices. So there will be a key that we will try to match against. And this key again can come from header fields or a combination of them, or it can come from metadata. So what is the metadata? It is intermediate data generated during the execution of a P4 program. So if you remember, there are several stages in the egress and egress pipeline. So when we are doing a computation, we can store that data for the next stage, and we can use on the next stage. So that's what we call metadata. And this diagram here is just another way to visualize what is happening. I think we have an example. I will come back to this in a second. But before that, there is a lecture that we will talk much more about metadata. For now, for this lab, I wanted to bring this without going into detail. So this is the metadata. Metadata is the intermediate data generated during the execution of the P4 program and has this type of information. Later on during the week, we will use this more interesting one. For example, NQ times time. We want to compute how much time a packet was in the queue, because we might want to know the queuing delay. So we will use this type of fields. I put here 3 examples of metadata. One is the ingress port. And what this means is what is the physical port the packet is coming from. Egress spec is the egress port to which the packet should be sent to. And egress port in which the packet is departing from. I mean, there is a subtle difference between these two. Again, for now, we will not go into these details. We will expand all these on, I believe this is on Thursday. So Vinicius have a question. Is there a programmable way to figure out how many table entries are supported in a specific switch? Oh, that's a really good question. So Ali has a comment here. It depends on the complexity of your P4 program. Some tables might be larger than others, so that the number of entries might differ. That's a good answer. I know also that Eli was, I think Eli, you were trying to figure out in some of your experiments what is the maximum size of the table for some of your experiments. Do you have any comment on that?
Yeah, exactly. I mean, what Ali said is correct. I mean, if you take an example, a table that matches on a destination IP address, that's a 32-bit field, right? Destination IP. But then you might have tables that will match on a combination of fields or a small fields. So the amount of entries you can store there really depends on the key size of your match, also the match type, if it is exact or LPM, which we will talk about also this day. And also about other stuff like, for example, the action data. So how many parameters are you supplying later on to modify some part of your P4 program? So unfortunately, there is no way to determine this programmatically. So in your P4 program, you can't know that. Based on what I did before was a simple matter of trial and error. So try first to, let's say, you write a program, you want to see how much you can have entries in a table. Start with some number, let's say 32,000, compile. If it compiles, then okay, this is a good value. Then you can maybe double it, try 64,000, and then you keep trying till it gives you the error where it will clearly state that you don't have any more memory or you don't have any more resources to compile the program. So it's more a trial and error kind of a thing. I'm not aware of any programmatical way to figure this out.
Thank you for that, Vinicius. Thank you, Eli. Okay, so that is metadata, but again, we will talk much more about this on Thursday. So this is with the example. I mean, and the reason why we use IP is because we're very familiar. We're familiar with routing tables. So the routing table is a match action table. So key, we use the destination IP address. So we try to match against an entry here in the first column. We are using exact matching, 32-bit matching here. If there is a match, there is an action to be performed. So we will forward the packet. Action data will be egress port 4. And therefore, here we have this output from this multiplexer. Okay. So if there is no hit, information will come from the default. So action code, I mean, we will write the code, egress port 4. That's what we're going to be doing. That is what our code will look like. And then we will do some other things such as TTL equal TTL -1, time to live, and potentially a few others. So this is just a simplified example. Before we go to the labs, two more things I wanted to mention. One is the controls, the other are the actions. So you will see in the P4 program controls. So for example, how to define your ingress pipeline. So, and you will use this control. It's similar to functions. Here we have similar to C functions, but just a clarification without loops. And again, why not loops? Because we are processing bits, they are coming at line rate, and we don't have that many stages. We'll change very quickly here to this. Remember, bits are traveling through the pipeline, and there are just these stages, stage 1 to stage n. They are practical implementation 20, 24 of those. So we cannot do such a complex processing because we will be running out of the hardware that can do the processing. We can declare tables and variables, and the functionality is specified by the keyword applied. So here we have my ingress. I suspect this is the ingress pipeline. Remember that we already parse all the headers, and we have the header fields in this structure. We can declare variables. Here we're declaring 48-bit variable, temporary variable. And what we're doing here is some few assignments to swap the source and destination MAC addresses. So this is the portion of the code, and then indicating that the egress port where the packet will go is the ingress port. So we are sending back the same way that this packet was received from. So this is how the code look like. So the other thing that we will be using in these 2 or 3 labs today is the action. So again, similar to C functions, we can declare them inside the control or globally. And we have, they have parameters, okay? In, out, or in, out. We have, again, the same example here, my ingress control, and inside my ingress control, we are declaring this function, this action, swap MAC, that is receiving 2 parameters, source destination, and is doing this, is swapping source and destination. And then we have the apply, that is from the my ingress control. So that's pretty much what we have to know for these 2 or 3 labs that we'll be doing today. So in lab number 5, we will use tables. Topology is, again, a simple topology, 2 hosts, H1 and H2. The IP address is the same as the one that we use in lab number 4. And we will be implementing a table that match on the destination IP address of packets using exact matching. And I think the next lab is going to be using longest prefix matching, which is the more common for routing tables. Exact matching is common, for example, for MAC address tables. So just giving some examples. And then if there is a match, we'll be forwarding the packet to an egress port. So that is the goal for this lab number 5. So at this point, I think this is the last slide. I will go back to our program. So we just finished the parser match action tables, and I think we can start with lab number 4. So I will let Ali Alsabe will be leading this lab number 4. So Ali, I will let you share your screen, and if you want to go over the reservation, and we can start.
Okay, thank you, Doctor. Okay, so yeah, so I'm in NetLab right now. I've already logged in, and I will go ahead and make a reservation, like we did yesterday. So we just click here and schedule a lab for myself. You will only see this before workshop, and the first one into before. And for this session, we're gonna be doing lab number 4. So just click on it, and I will find an empty slot. And Just make it. Okay. Just wait for a few seconds in case you're doing your reservation. Okay. So this is our topology. We only have one client. Everything is being done virtually. And I'll go ahead and split the screen. So this is the content of the lab. So if you want to unlock it and take it to the left side of the screen. And here I'll show the client. I'll just adjust the resolution of the monitor, just for better readability. Okay, so just as the same as every lab, in every lab is self-contained. So we'll have an overview objective of the lab, as well as the roadmap. And also for every lab, we have the section 1 is the introduction, which you will need to complete this lab, so you don't have to like go over the internet and like learn the theory. Everything is going to be written in section number 1. And in this section, for example, we're defining the headers. So here, for example, we have the Ethernet header because we're basically going to be implementing it in the P4 parser. We also show the IPv4, the standard IPv4 header, which we'll also implement, as well as the IPv6. So these are the standard headers. We also show here a screenshot of how we're defining these headers in P4. So this is a snapshot of the P4 program. We're going to cover all of that in while we're doing the hands-on session. This is just section 1. And later on, we'll also see how the programmable parser work, how the transition select statement works in the parser. We'll also be doing that. And this is the translation into the P4 program. You will see this definition of the states, also the transition, and so on. So just move to the topology of the lab. So in this lab, we also have we only have one switch and 2 hosts. The IP addresses of the hosts are written below the host. So this is the IPv4 address, and this is IPv6. And similarly, it's the same for the H2 with different IPs. So the first step of the lab is to launch mini-edit, which we use, is the emulator we use for this lab series. So double click on it. And the password is password. It's the same password for all the labs that we use. And in step number 2, I'll go ahead and load the topology. So we're working on that number 4. So file and open, and then I'll select the lab. And this is the .mn topology file. I'll just double click on it. And now once the topology is loaded in Mininet, you can run the emulation. So which is in step number 3. You click on the run button here on the corner left. So once these icons are grayed out, this means that the emulation is running, and you're basically now like a mini edit. These have their separate namespaces. So the first step, we will launch a terminal on H1. So hold the right click. You have to hold it and then select terminal. Now I'm inside the host H1. What we'll do in step number 2 is just test the connectivity between H1 and H2, just to make sure that like the there's no P4 program loaded, and there's no connectivity between the two hosts. So ping, and I specify the IP address of host H2, and then -C4 is optional, just to specify the number of requests to send or ping packets to send. And this shows here that like there's destination host is unreachable. And what we'll do next is basically start programming in P4. So in section number 3, the first step is to open a Linux terminal. So just minimize this. Double click on it. And then in step number 2, I will open code stands for Visual Studio Code. So I will open lab number 4 and I'll just maximize this. P4. Lab 4. So this here I'm opening basically in Visual Studio Code lab number 4. I will just I don't know, the screen is keeps getting maximized for some reason. We'll just adjust it. Okay. So now here I opened the Visual Studio Code in step number 2 by launching this command and specifying the folder or the lab that we're doing. This is just like the welcome file. I'm going to close it. So here, the step number 1, we're first going to code the headers. This is the headers.p4, and as we mentioned yesterday, we splitted the files into like different according to the different components of the P4 program, so that it's like easier to use and learn. So for the first step, we're gonna go to the headers file, which is open here, and we'll define the headers for the Ethernet, IPv4, IPv6, and so on. And just note here that this is like a simple lab where you basically define the IPv4 or parsing. And before you can customize or write your own parser or headers. They don't need to be like the traditional headers as we see in IPv4, IPv6. It depends on your program, on your network, and what do you want to do. But the flexibility here is that you can define and parse wherever you want. And so the first step number 2 is first we will define some type defs and constant. And type def stands for type definition. So for instance here, instead of writing bit 48, we can simply write MAC address T. Instead of writing bit 32, we can write IPv4 address and so on. And this is basically when we're writing P4, instead of like kind of memorizing how many bits a certain header is or a certain field is, we can just like we know that it's like in the MAC address, so we can just try this for simplicity. So under the first command, we will type the type defs. So type def bit 48 MAC address. T stands for type, which means like we will like this is the MAC address type. IPv4. This is the IPv4 type. And another one type def 48 IP4. Oh, 32. Sorry. Underscore T.
So
Yeah.
there is nothing to prevent you to create your own IPv4 address with 48 bits. I don't know why would you want to do that, but that's one of the really cool thing about programmable data planes. You can do it if you want.
Exactly, yeah. And now here we'll define a constant type IPv4. It's in hexadecimal, it's 0x800. So later on, when we're transitioning to IPv4, we can simply write the type IPv4 rather than just like writing the hexadecimal part. We'll see that later. So const bit 16 type IP. Usually constants are like all caps.
Ali, this is just your way to program. I mean, doesn't need to be like that, but yeah, it's just a good practice. That's what you are suggesting, right?
Exactly.
But it's totally up to the programmer. How do you want to write, the way that you want to code is up to the programmer.
Yeah, this is like all caps. It's just like we did it like that. Usually constants are like all caps, but you can define it wherever you want. Like here we wrote MAC address. You can write whatever variable you want, but just like for readability and just to when you're reading the P4 program, if there's like a bug or error, you can like read it more clearly. So now in step number 3, we will define the Ethernet header, which is the first header of like usually an Ethernet packet. So under the define Ethernet header, so the first to define a header, first you write the keyword header, and then the name of the header you wanna define, which is in our case we named it Ethernet _T because it's a type. So later on we will like kind of instantiate an instance of the Ethernet. So this is just like the header definition. And according to the, as we showed earlier, the Ethernet has 3 fields: the destination address, the source address, and the Ethernet type. And you can check them up, or I can basically show it here in the slides. So this is the Ethernet header as defined. We'll translate it into P4 format. So the destination address is the 48 bits, but instead of writing bit 48, we will just write MAC address. So this means like bit 48 destination address. And similarly, source address has the same bit 48 as well. So SRC address semicolon. And then we will have the Ether type, which is 16 bits. And again, these are like how many bits a field should have, and this is the name of the field. Like again, we named this because like it resembles this destination source, or you can give it any name you want. Now we will define the IPv4 header, which we also showed in our presentation here. So we just translate it to P4. Again, to define a header, these are like standard headers. We first write header IPv4 _T, and then first we have the version, which is 4-bit, 4 bits, and we have the header length 4-bit. We have the diff serve, which is 8 bits. We have the total length of the packet, which is 16 bits. We have identification, 16-bit as well. Bit 3 for the flags, 13 bits for the fragmentation offset, 8 bits for the time to live, and 8 bits for the protocol, 16 bit for the header checksum, and finally we have the source and destination IP, which have, instead of writing 32 bits, I will replace it by the type def that I defined, which is IPv4 address. Source, and I will name it source address because it resembles the source address, the source IP address. Similarly, the destination has same 32 bits, and I will name it destination address. So with that, we defined the IPv4 header type, and just like to, if you want to define your own header, you can do that. I believe the only critical thing is like when you're defining the header, it should be like multiple of 8. Like based on my experience, sometimes it's like it depends on the architecture for sure, but you have to be like careful because sometimes it needs to be like multiple of 8. Now we will define the metadata. So in this lab, we don't do anything with the metadata, but this is like a powerful tool or NP4, which you can basically use to carry data from like one stage or like one component from the parser to the ingress and so on. But for now, we'll just leave it empty. So we'll define it below the metadata struct. For the IPv6, we will define it later in the lab. We'll just like leave it now empty. And /* is just like it's just a command. It's like in C. And now once we define the metadata, we just left it empty. Now we define the Ethernet as well as the IPv4 type, but these are just like type. This is the type. This is not an actual IP header. In order, we need to group these headers based on the structure of the packet we're expecting. And in order to do that, we have to define a struct, and we will call it headers because this struct will basically contains all the header that we want to parse. So for instance, first we expect the packet to have an Ethernet header. So we instantiate an instance of the Ethernet type, and I will call it Ethernet. You notice like usually this notation type is just the type, and the instance doesn't have like _t, but this is just our notation or notations like used widely. Similarly, after the Ethernet, I'm expecting to get an IPv4 header. So IPv4. And with that, we basically defined our headers to contain Ethernet and IPv4 only for now.
So at this point, I want to make a pause. There is a good observation from Vinicius or question. Is there any recommended shared library or something similar that you could import instead of redefining well-known headers such as Ethernet, IPv4, IPv6? That's assuming that you don't need a custom header. So I know that there is a switch.p4 Eli or Ali. Do you want to talk about that?
Yeah, so actually, yeah, this switch.p4 program, which is available online, and like in the p4 org, they have a GitHub repository where they have like several examples. Like most of them, they contain these standard headers, especially like the simple switch.p4 program. So if you're, let's say, doing the P4 lab or like developing your own P4 program, you can like in our reservation, you can go to p4.org and
Do
copy.
you want to show switch.p4? Oh, actually, Lee, I think you just share right now. But I know that the switch.p4 you can get from GitHub.
I don't know if there's internet connectivity. Okay, there is.
Yeah, if you, at least I just Google switch.p4 and very quickly I found GitHub.
Yeah, it's here.
Yeah.
So you can simply, like, if you're inside NetLab and there's internet connectivity on this pod, then you can use the browser and to copy these headers. So header, let's see if they're here.
A few, one observation about using others code like switch.p4 is a whole already implemented switch implement the typical functionality of switch, or actually router, I believe, is that you are using a ton of resources in terms of memory that you might not need. But if you want to do that, certainly, yeah, that's something that will save a lot of time. So thank you,
Yeah.
Ali.
Mm-hmm. Okay, so now once we defined our headers and group them in our struct headers, we just go ahead and save, Control S, or like file save. And we'll go to the Parser implementation. And again, the Parser implementation is in a different file called parser.p4. But again, there could be all in the same P4 program. Like you can put the headers, the parser, ingress, and so on in the same file. So we'll go ahead and click on parser.p4. And as you see here, we included headers.p4 because we'll be using the headers that we defined earlier. So the structure header that we defined, like we will be using it here. And also as well as the metadata. But for this lab, the metadata is just empty. So we'll be focusing on the headers. So the first, in the parser, there's always the first state is the start state. And it's, as we'll see here, we'll define it. How do you define a state in P4? So first you have to write the keyword state. The first state is called start. And just like in this lab, the start state is just like transitioning to our first custom P4 state, which is like the parse Ethernet. But you can do other stuff in this start state. Like you can extract the metadata or standard metadata or metadata. So here the transition keyword is basically means to transition from one state to another. So I'm gonna transition to the parse Ethernet state that I'll define in a minute. And here I'm basically transitioning, or I'm moving to the next state unconditionally. So there's no, once the packet comes into the parser, it goes to the storage state and it will immediately go to the Ethernet state. There's no condition on going to the Ethernet. Now I will implement the parse Ethernet state here below. So again, to define a state, write the keyword state, and then I will name it parse Ethernet, same as I transitioned here. So in the Ethernet, first when you're parsing a packet, you need to extract the fields that in this state. So in parse Ethernet, we need to extract the Ethernet header. In order to do that, we extract from the packet. So the packet here is the incoming packet in our in the pipeline, and then you write dot extract, and you specify which header you want to extract it to. So in our case, header is defined here, so HDR, and then I want to extract the Ethernet. So I write just dot Ethernet in semicolon. And now in the Ethernet, once I extracted the Ethernet, I want to check the type of the Ethernet packet, whether it's IPv4, it's IPv6, or other types. So in order to do that, you have to do a condition like transition based on the Ethernet type. And the Ethernet type is just a field in the Ethernet header. You can use it because I already extracted. So once this is extracted, means that this is like now is valid and you can condition on it. So transition and select is, if you're like familiar with the C language, select is has kind of the similar notation. Here you specify on which field you wanna like condition header dot Ethernet dot ether type. Now, once you're conditioning on this, once this condition is evaluated, you want to specify which state you want to move to. So in case the Ethernet type is of IPv4, then I will move to the state parse IPv4. So type IPv4 is the Ethernet type. And this is the one that I defined earlier in the headers .p4, which is 0x800 in hexadecimal. So if this is a IPv4, I will go to the parse IPv4. And otherwise, like the default state is just to accept the packet, which means to exit the parser and to move to the ingress block. Now that we've defined our parse Ethernet state, we'll move on to define similarly, in a similar way, we'll define the parse IPv4 state. So again, we'll write it here. State, I named it parse underscore IPv4. And in the IPv4 state, I will extract the IPv4 header. So dot extract HDR, because we named it like this. And I will extract the IPv4. And once I extracted it, I will just accept, which means we will exit the parser and move to the next block. So with that, we can save the P4 program because we defined our headers, the Ethernet IPv4, and we grouped them in headers, and then we moved to the parser, and we defined our states. So now in the next section, what we will do is compile the P4 program, push it to the switch, and see and like try to send the packet from one host to another, and see what we will how the program or the P4 switch acts. I can pause for a few seconds if anyone has a question. Okay. So in section number 5, the first step is I need to compile the P4 program. So in the Visual Studio Code terminal, which is right here, you will write P4C, which is the P4 compiler, and you will give it the p.p4 program that you wrote. And just as a recap, here there are a lot of p.p4 files. So which ones you need to pass for the p4c command is the one that basically groups, like these are just like separate files. But again, basic.p4 is the file that includes all these p4 program and is the one that contains the main function. So this is the one that you will give to the compiler. Hopefully, okay. So we didn't have any error, any programmatical error. And now the P4 program is compiled, and as you see here, it generated a basic.json file, which we will push to the switch. So in the next step, we will push that JSON, basic.json to switch S1. Push to switch. This is just like a file that we wrote just to copy the files to the switch, the container. And it will ask for a password, and the password is password. Okay. So I will go back to the mini edit, and I will open a terminal on the switch. So I'll be inside the switch namespace, or like similar to the operating system. And first we will just validate in this step that the basic.json file was pushed to it. So write the command ls, which lists all the files. And here we see that basic.json is pushed to the switch. Now, the next step is just to verify or to display the interfaces of the switch. To do that, you will write the command ifconfig, just similar in same as in Linux to display the interfaces. So here you will have S1 ETH0 connected to H1 and S1 ETH2 connected to H2. So how, or just like a quick note on how did I know that like this is connected to H1 or H2? Basically, you can validate that using the links command. Just it shows you which interface is connected like to which interface. Just a quick note. And now I will go ahead and write this command, which basically launches the switch. The simple switch launches the daemon of the switch, and I will give it the compiled P4 program basic.json.
Ali, there's observation again. In the parse, if you go to the parser, your code, and the parse Ethernet state, what happened if an IPv6 packet is received? Does it match the default accept statement? Is it forward? So yes, it's gonna go through the default. It's gonna be accepted, but when it goes to the pipeline, if you try to access the header fields of IPv6, you will have an error. That's the best answer, but I don't know, Ali and Eli, you wanna add to that?
Yeah, I can add to that. So once an IPv6 comes, the Ethernet type will definitely not match IPv4 option. So it will go to accept. In particular, in this P4 program, we don't have like any complex like processing in the ingress control block. So basically, there is no like matching based on the IPv4 or IPv6 and so on. So the packet will be delivered as well, even without specifying type IPv6. But the reason is that like in the next section, we will write type IPv6, we will define an IPv6 and we will parse it. And we will do that just to show you like later on in the logs of the switch, how the switch is basically selecting. Is it like which one is matched in the parser? Is it the type IPv4 or is it the type IPv6? And which state it's basically transitioning to. So this is just like for showing later on in the nanolog or in the like debugging phase. But in terms of what the P4 program will do is it will be the same, but this is just because our P4 program is very simple and basic, because we're only focusing on the parser part.
Yeah, but I think this is beyond that, Ali. I mean, beyond our example. For our example is fine, but I think at least how the code is reading right now, it says that it's accept. So probably somebody who want to put a code IPv6, want to do something with IPv6, try to access a field in the IPv6 header during the pipeline is going to get an error because you didn't parse that. So in my opinion, it would be safer to code default reject. I don't know if you agree with that.
Yeah, you can definitely like reject the packet if you want to be like strict to IPv4 packets. Yeah, that's a good practice to do.
Yeah, the other observation here is from Istvan. What happens if both IPv4 and IPv6 are present? Will you need a selector? So do you want to address that?
We will cover that, and I will just like mention that. So later on, we will also implement IPv6, and we will we will add it in the header as well as we will put it in the like select if the Ethernet type is IPv4, go to the state IPv4. If it's IPv6, then go to IPv6.
So Istvan, yes, the answer is yes, you will need a selector. That's the right answer. Thank you.
Okay, so I will go back to the switch, and I was in this command. I was gonna launch the switch daemon. So simple _ switch, and -r stands for the interface. 0 is the port of this the P4, and I will map it to S1 ETH0. Another interface is port 1, which will be mapped to S1 ETH1. So P4 will read it as port 0, port 1, and so on. But in reality, it's switch S1 ETH0, S1 ETH1. And then I will enable logging by writing the command nalolog IPC bm log.pc. This allows me to see the loggings of what's happening inside the switch, which is very important if you're building even like a small P4 program or a complex P4 program. So now, once I enable the daemon and attach the interfaces, I will go ahead and push the table entries to the switch. So in our case here, write simple switch CLI, and I will push the rules which are specified in the lab4/rules.cmd.
So what Ali is doing, Ali, just something that I want to mention here. You are populating the table right now. So we will be covering in much more detail than how to populate the table at runtime, if I remember well. But basically, it's just adding some entries in the table, similar to what we do with a routing table. That's what we're doing at this step.
Exactly. And this, like the key action, will be explained in the next session. And populating table, like in runtime, how do you add them? I believe we will cover that tomorrow. So here we just like installed two rules. Briefly, these two rules, they match on the port, and the only thing they do is just forward it to the different port, to the opposite port of the switch. So if packet arrives at this port, it will be forwarded to this port, like H1 to H2, and vice versa. So now I will initiate the command nano message underscore client to display the switch logs. Nano message client. Now, like you see here. So what I will do next is that I will open host H2 terminal, or the right click terminal, and I will launch the command receive.py, which it will basically sniff packets on this specific interface. So once I send, and the next step, I will send a message from H1, and I'm expecting it to be displayed here. So I'll go to host H1 terminal and write the command send dot py. I'm sending IPv4 packet. I have to specify the destination, which is which is host 2, and just a simple message which is hello world. Okay. So I'm just showing you here that because we correctly implemented the P4 program and populated the tables, I was able to receive the message on the other end, which is host H2. And you can verify this from here. So more importantly, I want to show you, like we show here on step number 4, what happens once the packet is received as at switch S1. So I will go to the logging and the switch, and we'll explain that. So as you see here, the packet comes in through port 0, which we mapped it to interface S180H1 here. First, it gets into the parser, and this is the start state that we talked about. And then it transitions unconditionally to the Ethernet. So the first here, extract header, it extract the Ethernet header, and then it basically transitions to IPv4 because the condition on the type of the Ethernet matches IPv4. So it extracts it, and parser done, which means which translates to transition accept. This later on will be covered in the next session, but basically this is the next stage, or basically the next component, which is the ingress control. But our focus here is just on the parser. So in the next section, we will augment a P4 program to include.
When do we we are a little bit over time, and I just want to make a pause because we have been here for almost an hour and 30 minutes.
Mm-hmm.
Why don't we pause here for 10 minutes, and then we will come back and we will continue by implementing the IPv6 parser.
Okay.
And also perhaps it's going to be a good idea to show how to run the Wireshark, because at the beginning today there was an observation. What can we do to troubleshoot? We are not able to see the packet is arriving at the destination host. So let's make a pause here for 10 minutes. So right now is 10:24 Pacific time. So we will come back and we will continue with this lab at 10:34 Pacific time.
I will add the IPv6 header, the definition below here. Just follow the same thing that I did before. So header, we'll call it IPv6_T. So the first field is version, it's 4 bits. The second field is 8 bits for the traffic class. The third field is 20 bits. It's for flow label. Fourth field is 16 bits. It's for payload length. And after that, we have the 8 bits for next header, followed by 8 bits for hop limit. And after that, you will have 2 fields for the source and destination address. Each has bit 128. We just left it as bit 128, but if you want, you can replace it as we did here. So you can define a type def and write IPv6 has 128 bits. So it's bit 128 source address and bit 128 destination address. So now once the IPv6 header is defined, I will add it to the header structure. So go down, here we have the headers, and I will add it below IPv4. And this is just like adding the headers or grouping them in the same structure. Doesn't mean that all of them are going to be valid. It just depends on the parser and what you extract. So once I define the headers, I'll go to the parser.p4 and I will add the transitioning or the selector to the IPv6. So here in the Ethernet, we were transitioning based on the Ether type. We were only taking into account that the IPv4. We will add the type IPv6. And if that matched, I will go to a new stage. I will call it IPv6, which I will define in the next step. So now we have a selector, one condition on one field, and we transition to do different states based on the selector. So now we'll define the IPv6 state here, next below its command. State force IPv6 and packet dot extract header dot. I will extract the IPv6 and I will transition to accept, which means to be done with the parser. Okay, so once you are done defining the header of the IPv6, as well augmenting it in the parser, you will just save the changes by pressing Ctrl+S. And now we're ready to compile the new P4 program, push it to the switch, and follow the same thing as we did for IPv4. So in step number 7, I will compile the P4 program again, so it will generate a new basic.json. So now this basic.json is updated to include IPv6. And next, I will push the basic.json to the switch. This is the new basic P4 program. Basic.json. I will specify S1. which is the switch, and we'll ask for password, and the password is password. So again, I will go back to the switch terminal, which is here, switch S1. It's the last thing that we did was the nano message. So I will go ahead and press Ctrl+C to exit that. And what I do is that now currently the basic JSON file is like the switch daemon is still running, and it's still running. So in order, I need first to kill it, and then reload the switch daemon with the new basic.json file. So in order to kill the switch daemon, you will launch the command pkill, and then you'll specify what you want to, which process you want to terminate, called simple switch. Now, once you do that, you can launch the daemon again. So simple switch is the daemon. You associate the interfaces, 0, same command, S1, nano log, IPC. And just don't forget to include the basic.json. And the last command and is just like to run in the background. Now the daemon is running, interfaces are assigned, attached. I will load the P4 rules again. Simple switch CLI, and we'll give it the file in the directory lab4. The file is called rules.cmd. Same rules are pushed to the switch. And now we will launch the switch logs to display the switch log. Run the command nano message underscore client.python.py. And what I would do now is I will send from host H1, I will send an IPv6 packet. So it's not the same send.py file. We separated them into different files. So this one is called send underscore IPv6.py. And you will specify the IPv6 address we want to send to, which is BBBB1. This corresponds to host H1. Hello world. Okay. And as you see here, I sent an IPv6 packet. And I will go to the nano log, the switch logs, and we'll see what happened. So first, the packet comes in at port 0, which S1 we attached it. And then it will start with the parser state. The first state is the start state. It will extract the Ethernet header. And then in the Ethernet header, it will check the ether type, if it's IPv4 or IPv6. It will see that the packet is an IPv6, so it will transition here to parse IPv6 and extract the IPv6 header. And once it does that, it will transition to accept. So this is just like we added if we didn't add the IPv6, it wouldn't go to this state. It will just like go immediately to parser done. This is why we added IPv6 state, just to show you how the parser acts or transitions based on the select statement that we made. With this, we end lab number 4, which is an introduction to P4. I just want to show you, as Dr. Jorge was mentioning, just like opening Wireshark on the other end and seeing if the packets are being delivered or not. So if you want to open a Wireshark, okay, let's say that this is you're sending a packet from H1 to H2. For some reason, the receive.py is not displaying the packet. It could happen. The receive.py is just like a simple Python program that displays IPv4 packet, doesn't necessarily displays IPv6. You can customize it if you can just like open it, customize it as you want. But you want to see if the packets are being received or not. The simplest thing to do is on host H2, open a terminal on host H2 and write Wireshark. And here, Wireshark is basically captures all the traffic. So on host H2, you will see two interfaces, H2, H0, and loopback. I want to capture all the packets on the interface H2, H0, so just double click on it. And now, let me send packet. Oops. Okay, I sent two packets. The first one is IPv6, and the next one is IPv4. So you will see here that I'm able to receive the IPv6. This is protocol version 6. You click here, Ethernet. This is the Ethernet header. You will see the destination, source, IP type IPv6. You can also check the Internet Protocol version, like the different fields, so on. Similarly, you can check the IPv4 packet, the destination, source. These are like different fields that we specify in the send.py. So this one thing that you might need to check if the packets are like being received on the other end or not. Similarly, if you want to check on host H1, you open Wireshark within H1 terminal. I don't know if we need to cover more.
All right. Thank you, Ali. I don't see any questions here. So is there anything else that you want to add before we jump to match action tables?
I think that's it. I don't have anything in mind.
All right. Thank you. Thank you very much, Ali.
Thanks, okay.
So we just cover parser implementation. As you saw, is once we learn the main statements like transitions, and there is not that much, but the main statements, it's straightforward to implement the parser. And of course, we have to know the headers and the header fields. Now, we had in mind to have 2 labs on match action tables. I want to ask Eli and Jose, probably we will have time, Eli, for 1 lab similar to yesterday, and we can spend a little bit more. So which one would be better? Match action tables using longest prefix match or exact matching? So which one would you prefer to cover?
So the difference between lab 5 and lab 6 is that lab 5 demonstrates the exact matching on a table. In lab 6, we discussed the LPM, longest prefix match, but at the same time, we have exact match. So lab 6 kind of contains what lab 5 has.
Okay, so why don't we then go to, we cover lab 6, and we will describe a little bit more. What do we mean when we said exact matching and longest prefix match, for those who might not be familiar with those terms? Eli, are you going to be leading this, or Jose?
Yeah, I can lead this.
Okay, so I will let you share your screen.
All right. All right, so hello everyone. In this session, we're gonna be describing match action tables. we're gonna show how we can implement a match action table in P4. And the activity that we are doing here will be discussed in lab number 6 in the P4 Programmable Data Plane Switches lab series. So you have been seeing this figure for multiple times these past 2 days. And again, this is just how the architecture looks like, the V1 model. Now, the goal here is to implement tables, which are the main processing unit that allow you to perform some complex logic in the data plane. We all know that tables usually in traditional switches, you can perform switches and routers. You can have like flow lookup or routing or access control list. But in P4, we have the capability of doing a little bit more than that, right? So we can have our own logic where you can do some assignment of values. You can do some operations such as incrementing, decrementing, simple arithmetic. We're gonna be seeing some of these operations later on in this session. Now, but where does the tables reside in this architecture? So where we want to implement our P4 program, where should we implement the tables, the match action tables? And the answer to this question is in the programmable pipeline here. So it's either in the ingress, so that's the first part here, or in the egress. So Ali previously was discussing the parser. Now we assume that the parser will be implemented and the parser will transition to the right state and accept. But what happens after the accept? So we're gonna go to the ingress block, which is what we are seeing here in the first block, right? And there we're gonna implement the table and the actions for these tables. And based on whatever logic that we specify there, we're gonna be doing the forwarding, or we can do more than that. Now in the lab, we're only gonna be implementing the match action table in the ingress. So we're gonna keep the egress empty, but for some application, for some specific use cases, you want to implement tables at the egress, and we will talk about that in the last 2 days of the workshop. But for now, we're just going to implement the table in the ingress pipeline. And in other words, it's the ingress of P4 file. So what is the objective and the topology of this lab? So now we have a slightly different topology. Instead of having 2 end hosts, we have 3. We have H1, H2, and H3. All 3 hosts are connected to a programmable switch. Here it's S1. And the goal here is to implement the match action table. And the match action table will have 2 match types. So, or let me be more specific, we're going to have 2 tables. The first one will have the exact match. And what do you mean by exact match? It's that it's going to look at the key and exactly will take that key as it is. So if we have a 32-bit value, we're going to have an exact match on these 32-bit values. And whenever we have a match, we will execute some action. In this specific lab, we're going to be forwarding the packet, and this action will assign the output port of the match IP address. We're going to do some modifications to the headers, specifically in the MAC address. We're going to modify that. And then we're going to also see how we can change the time to live field in the IPv4. And specifically, we're going to be decrementing it. Now, this is for the IPv4, but the same thing will happen for another kind of match. Sorry, the IPv4 exact, but the same thing will happen for the IPv4 longest prefix match. And what do you mean by LPM? Longest prefix match, it's kind of, if you probably all are familiar with IP addressing. Let's say you have 192.168.0.0/24. What if I want to do match on this whole network instead of just an exact IP? And using longest prefix match, we will be able to perform matching, and this matching is going to be considering a whole network. But this doesn't have to be only on IP addresses. It can be basically on other kind of fields, right? It can be some custom field that you want to implement. Okay, so in summary, we're going to have 2 tables, one that will perform exact matching on the destination IP address, and one that will perform longest prefix matching on the destination IP address. Now, both tables will be sharing the same action, which is basically performing the forwarding. And the forwarding here is not going to only be assigning the output port, but we're going to do some further modifications to the packet headers. All right. At this point, now we're going to go to the platform. So again, this is NetLab. I will go ahead and make a new reservation. So new lab reservation and schedule a lab for myself. And then we want to make sure to select the intro TP4 programmable data planes. And there we have lab number 6, right? So this is the match action tables part 2. We go ahead and click on that. And there we'll find some empty pod here. Just click on the red line, select for how long we want to schedule the lab, and then submit. We have a message, it's successful. At this point, our lab pod is ready, so we can go ahead and enter to the lab by clicking on the Enter Lab green button. All right, so now the pod is initializing. Just wait a few seconds and you will see the topology, which consists only of a single client. But again, this is the VM where we're gonna be emulating the whole P4 and the other host in Mininet. Okay, so like we did today and yesterday, we can undock the contents of the lab, put them on the left-hand side of the screen, and on the right-hand side, we will have the platform where we're gonna be issuing all the comments. Okay, so this is lab number 6. Again, same as before, we have a table of content, we have overview, the outcomes or the objectives of the lab, the settings. Similarly to the previous labs, this is gonna be password. So the default password is password all small caps. And of course, we have the introductory part, which will describe what is this lab about. So here we are describing what is a match action table. We're also showing what is LPM. So specifically when you have something like this, so you have an IP address and you have /29, 24, 8, whatever value that you have there. And we want to match on all the addresses that belong to this network. So this is what LPM is about. Okay. We also see here a screenshot that shows you know, a sample code, but I'm gonna skip this since we're gonna be going over it in detail while we do the steps. All right, so starting from section 2, this is where the hands-on session starts. So I'm gonna go to the client. Also, I will change the monitor's resolution just to make it a little bit clearer. And then, so this is the topology that we will have. 1 P4 switch, 3 end hosts. You can see here the interfaces. We're not gonna redo the topology from scratch, so we're gonna load it from the previously saved ones. The first step is to launch mini-edit, which is on the desktop. And there we can start by doing the topology. So here, the default password is password, right? You can see it here. And then we're gonna open, so file, open, we will navigate to the directory lab 6, and we're gonna open the lab6.mn topology file, which will have 3 hosts and a P4 switch. Next, we will start the emulation by clicking on the round button. Now the emulation started. We are ready to start issuing commands and do whatever we want in that topology. So the first thing we're gonna do is we're gonna go to the terminal of host H1. So right click, we hold the right click and then terminal. And from there we can check the interfaces. So here, for example, if you type ifconfig, what you're gonna see is we have H1-ETH0. This is the IP address 10.0.0.1. And the mask is 255.0.0.0, which is /8. And also we can see the MAC address, which is all zeros, and we have 1 at the end. All right. Next thing, we're gonna start by doing the P4 programming part. So I will minimize. By the way, you can see now I think this happened to one of the attendees, so I lost focus on the screen. If I try to undock this and dock it again, now it's working. Okay, so if that ever happens to you, just undock it and dock it again. All right. So let's minimize all the windows and then launch a new terminal here on the desktop. So double click on terminal. And then we're gonna start the development environment by using the command code to start the Visual Studio Code and specify the working directory, which is P4 labs. And specifically, we are in lab number 6. So now the Visual Studio Code will open and we're gonna be in the lab 6 directory. All right. So what is happening here is that, remember, we start always with the parser, but in this case, the parser is already written for us, right? So we are parsing IPv4. We're not going to change anything in the parser, but we're going to implement the match action tables. And as we said during the slides or the presentation, this is going to happen inside the ingress block, right? Which is here in a control called my ingress. Now, as you can see, we have this control, we have the definition, but it's empty, so there's nothing there. And our job in this lab is to basically fill this control by adding the tables and their actions. Okay, excuse me for that. I have to rechange the monitor settings. This is happening for some reason here. All right. So what are we gonna start first with? So in P4, when we want to write tables, the tables will have actions, right? The table will be used for matching on a certain field. And then when we have a match, we're going to execute some action. Now, when we start writing the code, we want to make sure that we start with the actions. So we have to declare and write all the definition in the actions. And then later on, we have to write the table definitions. And this is why I will be starting now with the action instead of starting with the table. Now, what are the actions that we want to do here? So the first one would be to forward the packet. And in the forward, we're going to be doing a few steps. So it's not only specifying the output port. Specifically, first, we're going to be specifying the output port for sure, because we're going to forward the packet. But then we're going to be updating the source MAC of the packet with that of the previous destination, right? So in other words, if you look at it here, so if I'm sending from H1 to H3, what I'm going to do is I will assign the output port to be this port here so that it goes to H3. But now the source MAC of the Ethernet here is going to be equal to the destination MAC that was in the previous packet. And the nice thing about P4 is that you have the flexibility to do these kind of assignments. You can do also arithmetic operations. So you can define the logic, whatever that you want to do inside these actions, right? So in this logic, we are simply updating the source address. So the new source address of the packet to be equal to the old destination address, right? And then we're going to change the new destination address to be equal to that of the receiving host. So for example, if you are sending from H1 to H3, the destination address now will be equal to the MAC address of H3. If you are sending to H2, it's going to be equal to that of H2. And then we're going to be decrementing the time to live field in the IPv4. So there are a few things to notice here. First, when you want to access some field inside a specific header, we have to start first by specifying which header we want to access the field from, right? So these source address and destination address, these are the MAC addresses. And therefore, we have to specify first header.ethernet. Whatever field that we want to access from Ethernet. Time to live, for example, is in the IPv4 header. So we have to specify header.IPv4. Okay. So now there are other stuff that might still not be clear at this point. Specifically, where are we gonna get the MAC address of these destinations, H2 and H3? And where are we gonna get the information on which port to specify as an output port? Right. So you can always hard code everything in the P4 program, but this is of course not a good idea because you have complex topologies. You might want to be doing all this stuff at runtime. And the idea here, whenever you declare an action, you can specify parameters to this action, right? So in this case, I'm saying that I have an action called forward, and it receives as parameters a destination MAC, and it receives as parameter an output port, right? The output port here in this specific architecture, the V1 model, has the type egress-pack. Egress-pack-t, so _t. So this is the type of the output port. So again, I'm declaring a new action. It's called forward. So I called it forward. You can call it whatever you want. This is the action name, but action here is a keyword. So you start with action, the action name, and then the parameters that you are planning to pass later on from the control plane. So what am I planning to pass if I want to do forwarding here? I want the destination MAC of the receiver, and I also want the output port. Now, if I have these two variables, then I can assign them to the right headers and to the right metadata in our program. Now, let us start with the first line here. So we have standard metadata.egress-pack equal to port. This means that the port that we specify from the control plane, right, will be assigned to a field called egress-pack, which is part of the standard metadata. And Dr. Jorge, at the beginning of the day, he mentioned that there are some metadata that are available by the architecture, and these are fixed metadata. They are standard or intrinsic metadata. And the goal is to provide you with some fields that you can use so that you instruct the traffic manager what to do with a packet. Now, obviously, one of the most easy and useful fields is the egress-pack. Egress-pack specifies the output port. So if I go back to my architecture, I'm instructing the traffic manager here, right, which port to be using to forward that packet. Okay, and you do that by assigning the value of the port to the egress-pack. Okay, and again, this value, we are getting it from the control plane. Now, next, we are assigning to the source MAC of this new packet that will leave from our switch, the value of the old destination address in that packet, right? So the old destination address in the Ethernet will be now the new source address in the new frame. And then the destination address of that frame will be equal to whatever we decide from the control plane to specify, right? And this is why here this destination address is equal to this one. So I'm taking this one here and putting into the headers. And note that whenever you see header.ethernet equal, it means that now I'm changing the headers in the packet, right? I'm doing some modifications. And finally, I need to decrement the time to live. So if you think about it here, it's more like how a simple router would work, right? And the way to decrement it is simply by subtracting 1, right? So the new value of the time to live is equal to the old value minus 1. And imagine now, if you just see these simple instructions, the amount of power you have in P4 in terms of modifying the headers, arithmetic computations. You can do plus here, you can do minus, you can do bit shifting, for example, if you want to multiply or divide. You can do a lot of things. You can do concatenation, you can do bit slicing. There's a lot of things that you can do in the actions, right? And if you want to compare wherever we are seeing this to a legacy or a fixed function device, we can see now how much capabilities and power we have. Dr. Jorge mentioned yesterday VXLAN, for example, how it took a lot of time to be implemented. If you know P4, you can simply implement it in a few lines of code and then you have it ready. All right. So this is what we're gonna be doing now. We're gonna start by typing in this action in the ingress block. All right. So action forward. This is the action name. And then we specify here a MAC address type, destination address. And again, this MAC address type is the one that Ali was writing in the previous lab, right? You can always write here bit 48, that works well. And then we have the egress spec. Egress spec is part of the, it's just another word for bit 9. It's a 9-bit field to specify the output port. Okay, and then inside this action, we're gonna specify the output port, which is part of the standard metadata. The standard metadata, we got it from the headers of this function, right? Or from the signature of this function. So standard metadata dot egress spec is equal to port, right? And then header dot ethernet dot source address is equal to header dot ethernet dot destination address. Now header dot ethernet dot destination address will be equal to whatever we specify from the control plane, which is this value here. And finally, we will decrement the time to live field in the IPv4 header.
So Eli, there's a question. Can you also use conditionals like an if inside an action block?
Yes, yeah, you can do that. The only thing that you have to keep in mind is that in hardware, if you program for a target like Tofino, you want to make sure that you don't excessively use them because you're going to be running out of resources. But here it should be fine. You can use it well. And there are other ways to use this if, and we're going to show one in this lab. Basically, later on, we're going to see how if we have a miss from one table, to how to apply the second table. So it's kind of simulating how an if statement works. Okay. All right. So now we have our forward action implemented. And by the way, if you want like to read further about it, all of the description that I was talking about is here. We're going to do another action, which is drop. And all this action is doing really is assigning a value to a flag that the traffic manager will read. And if it's set, it's going to be dropping the packet. So I'm going to call the action drop. We don't need to specify anything from the control plane. So that's why we kept here the arguments, argument list empty. But what we are calling here is mark to drop. This is just a primitive that is available for you from the architecture, and you pass to it the standard metadata. So what is this mark to drop here doing is simply, again, setting a flag. And this flag will be read by the traffic manager. If it is set, the packet will be dropped. It's not going to be forward, right? So, but now there is no entry point. So we are not describing what happens as soon as the packet enters. I'm just, it's as if you are in a C program, you are declaring functions, but we didn't invoke any of them. So I'm saying we might forward, we might drop, right? But next we're going to see when we create the table and we create what we call an apply block, we see how the sequence of these are going to be invoked. All right. So now that we have the actions ready, we can start by creating our table. We're going to start first with the exact match table. And this table will be matching on the destination IP address and the packet. So what is the syntax? First, we start by typing here table. So that's a keyword to specify we are creating a new table, and you give it a name. The name here, we are calling it IPv4 exact, but you don't have to add exact or anything like that. You can call it forwarding, you can call it whatever you want. So when creating a table, there are a few things that we have to fill. First, we definitely have to specify the matching key. So we write key equal, and then we have these curly braces. And the reason we have the curly braces is that the key can be composed of multiple fields, right? So we can have a concatenation of a destination address and who knows, maybe a source address, and create a large key that you want to match on. And this simple example here, we are just using destination address. So all we have to do is just write here the field name that we want to match on. So header .ipv4 .destination address. So this is the field that we want to match on. Next, we have to use colon here and specify the match type. So how are we going to match on it? Are we going to have exact matching on the value of the destination address, or we want to match on the whole network, like what LPM does, the longest prefix match? In this table, we're just going to be dealing with exact, so you write exact. And exact here is a keyword in P4, right? So you want to make sure you write exact here. Now that we have the key, so the table knows how or which field to match on, now we need to specify what are the possible actions associated with this table. So actions equal to curly brace. I think we have a question. So
yeah, Eli, the question is, can we have a table with empty key and or 0 size? Then leverage the default actions to do match everything like strategy.
Yeah, you can do that. Yeah, for sure. Yeah, and there's something like called also like default constant. So if you wanna specify what are the parameters inside a certain action, if you don't want to specify anything from the control plane with a key or anything like that, you can do that as well. But I don't think we're gonna show that here in this in these 5 days. But you can always try it. It's simple, easy. All right. And then, so we can specify now the list of actions. So again, we need to say that our forward action that we just created is part of this table. At the same time, our drop action is also part of this table. So here I'm just listing the name of the actions that we created. If you call this, I don't know, IPv4 forward, you have to write here IPv4 forward. So these should match. Then another property for the table is the size. And the size here specifies how many entries at most this table will be holding. And by entry here, we mean, for example, in this table here, how many destination address this table will contain with their corresponding action data. Right? So if we say 1024, it means that I cannot add more than 1024 rules inside this table. And then we have default action. So this is to specify for the table what happens if we have a miss, right? So we decided to match on the destination address, but there's no rule in our table that has this destination address that we see in the packet. So what happens in this case? So you have to give it a default action. The default action in our case is drop. So this means that if we don't have an entry in our table that matches the destination address of the incoming packet, we want to set the flag in the traffic manager to drop this packet. So we don't want to forward it. In other words, only the rules that are there are allowed to be forwarded. And basically that's it. So this is how you create a table and how you specify what actions are associated with the table. But it's still till now, it doesn't have a flow. So we don't know what happens. Is there like a starting point for this ingress? And this is what we're gonna be doing later on. Now, before we start by specifying what is the sequence of the execution here, we will create another table, but this time it's gonna have a different types of matching. It's gonna be doing an LPM, longest prefix match on destination IP. So it's really similar to the previous one. You'll start by table, you give it a name. We're gonna call it IPv4 LPM. And then the key, this is gonna be the same. Header dot IPv4 dot destination address. However, now the match type, this is gonna be LPM. Okay. Now LPM again is longest prefix match. This will allows us to do a matching similar to how when you match on a network address. I have to mention though, there are you don't only need to use LPM for network addresses, you can use it for something else, but also the architecture can provide different types of matches. For example, you have if you want to match on a range, let's say between two different values, some architectures provide that, but not all of them. right? So you have to see the architecture specification. So for example, some will be supported by the Tofino native architecture, but not in another architecture for a different vendor, right? There's also kind of a ternary match. If you want to do that, it's also possible. But again, you have to see the capability of the hardware.
And for those who are not familiar, because we keep repeating Tofino architecture, Tofino native, or Barefoot Intel, we are referring to a commercial switch that you can buy, purchase, and then program. And I think it's the most popular programmable switch in the market right now. That's what we mean when we said Tofino architecture, Barefoot switch, or Intel switch. It's all the same. It's this product that is in the market, and it is the most common programmable switch today.
Yep, exactly. All right, so now same thing. We're going to specify what are the actions associated with the table. So you can have other actions for this table. You can keep creating actions and associate them. In this case, we're going to use the same actions because logically we're doing the same operation, either forward or drop. And usually the less actions you have, it means, you know, the less complex your program is. So if two tables have the same functionalities, it's a good idea to use their actions, similar actions. So I listed here that in the actions we have forward and drop. The size also. And by the way, we had a comment today about like how to determine the size, or this is what I was talking about, where I was trying to enlarge the size, compile, and then see what happens. Now, I have to mention that in the software switch, the MV2, the one we're using, this is not going to be a big deal, but in hardware targets, you will have some limitations, of course. And then finally, the default action. This is also going to be to drop the packet if we have a miss. Okay, so if I want to review what we did so far, we wrote an action to forward, an action to drop. We also wrote two tables, one that will perform an exact matching on destination IP, and the other will perform a longest prefix match on destination IP. But so far, we didn't specify which table to be activated, or what is the sequence of these tables to be activated. And every ingress and egress block will have this apply portion in the code. So you will have to write apply. And this is where you basically specify the sequence of table applying or execution. And here you can have some conditions. You can have also some other arithmetic operations. So it's possible. But essentially what we're doing here is we are doing a condition first to check if the IPv4 header is valid. What do you mean by if header.ipv4 is valid? If we parse the IPv4 header, right, there would be a flag set saying that this header.ipv4 is valid, right? So at this point, let's say you received an IPv6 packet, right? This if statement will not match. But if you receive an IPv4 packet, because you did the parsing and you transitioned to accept, since this parsing was successfully reached for the IPv4 state, then what's going to happen is that this is valid will be true, and then this if statement will be executed successfully. So you will go inside that if statement. So again, where do we set the validity? It's by parsing the header. Now there are also something called set valid, which we will not gonna talk about now, but it's basically to explicitly set a validity for a certain header. This is useful if you wanna, let's say, create new headers and in the P4 switch and then push them. So you'll be adding more headers inside the P4. But for now, we are just checking if we successfully parsed IPv4. So if that's the case, we go inside it and then we execute this if statement. And what we have here is we start first by applying the IPv4 exact table. And by typing here IPv4 exact, which is the table name, that's the first table that we created, dot apply. So when we do that, it means that this is where we're gonna be basically applying and looking for the key and executing the actions, right? And what we are doing Further, we are saying .miss. So in other words, I'm applying the IPv4 exact table, but if we have a miss, I will go and apply the IPv4 LPM table. So the priority here is for exact, right? If you have an exact entry for that IP, you will just use whatever you do in that IPv4 exact table. However, if there is a miss, and miss here is a keyword, right? In other words, so we don't have an entry for this IPv4, then we will try to do it for the IPv4 LPM. If we have an entry, then fine, the action forward will be executed. If we don't have an entry, the miss will be here taking place, and therefore you will be dropping the packet. So to summarize, first we need to check the validity of the header, then we need to apply a table, but also we can check if there's a hit or a miss. If there's a miss, then we can basically execute another table. And by the way, this is the logic that we wrote. It doesn't mean that that's the only one. Maybe you just want to write IPv4 exact.apply, and then immediately after it, IPv4 LPM apply. The compiler will not complain. But this is usually a good idea. You only want to apply another table if the first one is a miss, and only if these two are related, right? So later on, for example, you can have a sequence of other table executions and it will work fine. So always, if you have a code, you know, if you want to read a P4 code, it's a good idea to start with the apply, right? Because here you're going to see which table is being executed and what kind of actions are associated with the table. So this is kind of the small main part of this control block that will be showing the sequence of execution of tables.
Ellie, there are question or should you has a observation or question?
Yes. Hi. So in this apply function, there's the one you are highlighting .miss. Before that, there's an apply. That apply, is it in the architecture?
Can you say the last bit? Is that apply what? I'm sorry, I didn't hear you.
Oh, so where is this, you call it a function or something apply, where is it?
Yeah, that's a great question, actually. So this apply is associated with any table that you create in your P4 program, right? Every time you create a table, right, there will be a function that is called apply. And when you invoke that apply, it means that now you are doing the matching on this table. You don't explicitly create apply. This is already provided for you, right? As soon as you create a table. So this is already there, but you don't define it anywhere. And so what's going to happen is you have this IPv4.apply or IPv4 exact.apply. When a packet comes, this is going to go here and try to do a matching on this key. Do we have a hit? If we have a hit, then we're going to go to the forward, and there it's going to be doing all the action code that you have there. If you have a miss, then you're going to go now to this apply here, where you're going to be matching on the destination address, but now using the LPM. If you have a hit, you have forward. If you have a miss, then you drop.
And the reason because why you're dropping is because of the default action of the longest prefix match.
Exactly.
Table.
Yeah, exactly.
Mm-hmm. Thank you.
All right. So let us type in the apply. So if header.ipv4.is valid, then we check for if IPv4 exact.apply.miss. We have IPv4 LPM.apply. Okay. And always make sure to save the program. All right. So all we did here is just fill the ingress because the parser is already written, right? But if you are starting from scratch with a skeleton P4 program, you want to make sure to fill the parser based on what kind of fields you're planning to use later on in your ingress or egress, right? You fill the parser, then you fill the ingress, and if you want to do more than that, you have to do it as well. Now, before we proceed, also, if you noticed, we modified some fields in the headers. And usually it's a good idea when you do these kind of modifications to make sure that the checksum, which is a field inside the header, is recalculated and reset to the correct value inside the header. We're gonna describe this tomorrow. There's a session on that, right? But for now, we're just gonna be looking at writing this ingress block. All right. Next step is to compile. So P4C basic. Let's see. All right, then we can see that we have a JSON file generated from the compiler, which will be the data plane specification. And therefore, we have to push it to the switch and load it there. So push to switch, the file name, which is basic.json, and then the switch name, which is S1. The password is, as usual, password all small caps. All right. Now, the next step is to go to the switch and then load that data plane specification and run a daemon there. So I will maximize mini edit to see the topology, and then go to the switch, right click, hold the right click, and then terminal. To verify that the file was pushed successfully, we can issue ls, we can see basic.json, and then we need to start the daemon, but we need also to specify the interfaces, right? When we allocate the ports. And it's a good idea to start with ifconfig to see what are the available interfaces. Remember in the previous labs, we had two interfaces, S1ETH0 and S1ETH1, but now because we have 3 hosts, we have 3 interfaces, right? So ETH0, ETH1, and ETH2. All right, and now we're gonna start the switch daemon and we're gonna specify all these 3 interfaces. So simple switch, this is the same command as before, but we are adding a new interface here. So first 0, this is gonna be S1 ETH0, and then 1, this is gonna be ETH1, and then we have 2, S1 ETH2, and then for debugging, we're going to enable the nanolog, specify the socket file for interprocess communication. It's going to be in temp, the mblog. By the way, you can specify other files. You don't have to stick to this one, right? And later on, when we start the control plane interface, it will automatically read this socket file, and you don't have to specify it later on either. So just specify a name here.
And Ellie, do you want to remind us the parameter -I and 0 at S1 ETH0?
Yeah.
You explained yesterday, but I think it's good to remind everyone again.
Yeah, sure. So the idea is when we start the switch daemon, we want to make sure that you tell the switch daemon, because remember, this is just a software, right? You need to tell it that the physical or the actual interface in Linux is a certain port number that we will be using in our program when we need to assign, for example, an output port, right? And the switch, because this is a program by itself, it doesn't know about the interfaces, or even if it knows, it doesn't know which one to use. So you have to explicitly say that when you start the daemon, that S1 ETH0, which you see on the left-hand side here on the topology, is going to be referred to as this one here. This is going to be referred to as port 0 whenever you deal with ports at all in your switch program, right? And then S1 ETH1, this is going to be port 1, right? So as if you have a logical port here, port 1, and here logical port 0. And then you have S1 ETH2, which is on the right-hand side, and this is going to have a logical port 2. Now, I'm saying logical port here because later on, if you want to install rules and tables, you don't specify the output ports by using S1 ETH2 or ETH1 or ETH0. You specify them by port 0, port 1, and port 2. All right. I think we have a question. Thank you for the review. Question, is it possible to have a conflict with system port when assigning? Let's see. So basically, this S1 is just an interface that was created using IP link. And this is all part of the IP route 2 package. It's not connected to anything else, right? So there's no connection. I believe that if you want to attach an interface, it shouldn't be connected to another software. Otherwise, the operating system will complain about it, right? So you want to make sure there is no kind of a link there that is already being used by another process. Otherwise, the operating system will tell you that, okay, you can't use this. But these S1 ETH0, S1 ETH2, and ETH1, you are seeing them here because when we modified this mini edit version here to include before, every time we add a new link, there is a command somewhere here in the background allocating these interfaces, right? And therefore, the number of links that you have connected to the switch, you will see their corresponding interfaces, right? You can obviously do all of this, you know, without having mini edit, right? But then you would need to know how IP link works. And when I say IP link, it means this is the Linux command under the IP route 2 package that will allow you to create interfaces, virtual Ethernet, for example. It will allow you to specify a link between two virtual interfaces. Right? But fortunately, with this interface of mini edit, and with the little tweaking that we did, we are doing all of this, you know, without having to do all the tasks manually. But it's a good observation. All right. And then, so we specified the interfaces, we specified that we need logging, and of course, we need to specify the data plane specification, which is basic.json, and we're gonna launch it in the background by using this and at the end of the command. Okay, and you can see it tells you that S1 ETH0 is now recognized as port 0, this one is port 1, and 2 is port 2. All right, next step is to push the table entries to the switch. And again, we're not gonna be doing them manually. This is gonna be tomorrow. We're gonna show you how to write all these commands to populate the tables. But for now, we're gonna just assume that there's this file that is already created for us that contains all the rules. And we're gonna basically push them to our switch. And I will explain.
Ellie, and what you are showing there, basically, just a little bit more information. It's just an entry, a route entry in the table. For example, what I see here, the first one is 10.0.0.0/8. So it's just an entry in the routing table. Entry.
Yeah, exactly. This is this is what I was I'm planning now to explain. I will explain all these, but I was saying that this file here, rules.cmd, is just a regular text file. This is what we're not gonna explain now. We're gonna do it tomorrow, but I will of course describe what we are seeing here. So let me just push that file and see what we get in the output. First, you can see there are 3 entries, right? Each time you see this is one entry, this is another entry, and this is another entry. So we have 3 entries. And what we can see here is that we are adding an entry to an LPM match table that is called IPv4_LPM. And this table is part of the myIngress block, right? This makes sense. So all of this is part of the myIngress. Then let me just undock and dock again. All right. And if you go here, you can see this is the myIngress, and this is the IPv4 exact and the IPv4 LPM. So, right. So the first entry that we're adding is to the LPM table, right? The match key is A000000/8. What that means is this is the hexadecimal value, but if you convert it to decimal, this is equal to 10.0.0.0/8. So I'm matching on a whole network, which is 10.0.0.0. And I have to clarify again that this host H1 will have the 10.00.1, H2 will be at 20.00.1, and H3 will be 30.00.1, right? And by having a rule like this one, I'm saying that I want to match on all the IP addresses belonging to 10.0.0.0/8, and therefore H1 is part of that. Okay. Now, what is the action that I want to associate with this match? So the action name is forward, right? And I want to specify as parameters to this action these two values. What are these two? If we go back to the action definition that we have, right? The forward accepts two parameters. So first is the new destination address, and then is the output port that we want to forward the packet from. And so if we go back, what I'm saying is if we have a match on 10.0.0.0/8, right? I want to specify that the new MAC address is equal to all zeros and then one at the end, which is the MAC address of the destination here, H1. And the output port is 0, right? Again, this is just in hexadecimal. But what we are saying is if we have a match on 10.0.0.0/8, use this output port here, and the new MAC address is equal to this value. So this here MAC and this port will be received to this forward function, right? Or action, and they will be assigned to whatever logic that you describe here. In our case, we are changing the Ethernet header, and we are assigning the port to the traffic manager to know where to forward the packet. All right. And then we have another entry. So this is an LPM as well. Also, it's the forward, but now we are matching on 14.00.00.0/8, which corresponds to the network 20.0.0.0/8, right? And now what we are saying is, if we have a match, use the destination MAC equals to 2 at the end, and then the output port equals to 1, which is this link here. And then we have a third entry, but this one is for the exact table. So this is IPv4 exact. And you can see here, it will show you on the match key what is the match type. So the first two were LPM, now it's exact. It's exact 1E000001, and this corresponds to 30.001 in decimal, right? And if we have a match there, we have the forward action executed. The destination MAC would be that of host H3, and the output port would be 02, which is this output port here. Okay, it might seem a little bit confusing, but it needs some practice to figure out what kind of fields you have to supply from the control plane. You always have to think about it when you create a table that has actions. Are those fields that will be changing? Are those fields that will need to be populated? If not, if you have like few constants, you can simply put them here in the before program and there will be no problem. However, if this has to be changed and would be populated later on at runtime, then you have to specify them as parameters so that you can have the flexibility once you run that daemon to change how your before program will be reacting to the packets. Okay. And then next, we're gonna start our debugger. I think we have an observation or a question.
Yeah, there is a question. How do you configure set the traffic manager again?
Okay. So in this lab, all we are doing in the traffic manager is just telling it that use this output port to forward the packet, right? And the way we do this is just by specifying here what is the output port. And the output port is part of this standard metadata, and it's called egress spec. So when you pass from the control plane, for example, the port equals to 1, then this port 1 will be assigned now to the egress spec, which is read by the traffic manager. And we are doing this because this is a really simple example, just forwarding. Now, if you remember, we talked about it yesterday, the traffic manager is configurable, but not programmable. So I cannot change how the traffic manager is really doing things, right? It's just something that you can configure. Currently, we didn't configure it yet. We just specify the output port. However, there are ways to do more than that, and we're going to talk about them in the last 2 days. In the runtime configuration, we will be able to specify parameters, for example, related to the traffic rate or to the buffer or queue size in the P4 switch. And this is where you're going to be doing the configuration for the traffic manager. But for now, you just specify this value to tell it to out of which port this packet should be sent. All right. Okay, so the next step, we're gonna start the nano message client. I think here we have a typo. You just type in nano message. You don't need the /. Okay, and you can see that it automatically obtained that socket that we used when we started the daemon. Right, and then on host H2, we're gonna go and open a terminal. So right-click terminal, then we'll execute the /receive Python script. And then from host H1, we're gonna send a packet to 20.00.1 with the payload hello world. So let's go back to the terminal H1, and there /send of py, then 20.00.1 hello world. And so what happened is we sent a packet. This is an IPv4 packet, right? You can see all the information here. It has a payload hello world and it has its CP header. But in our program, we just cared till the IPv4 header, right? So we didn't parse anything beyond that. So let's go to the switch logging and see what happened there. So I will maximize here the behavioral model tab. And you can see, as usual, package is received. We have the parser being executed, basically what Ali described before. But then we have the pipeline start, which is the ingress, right? We have first a condition that is being evaluated. And this condition, if we go back to the code, this is refers to the if statement that we have here that checks for the validity of the header. In our case, it returned a true. This is because we parsed IPv4. So the IPv4 is a valid header. But then what happened is we have a table that is being activated, right? We have a miss, okay? And whenever we have a miss, what we do is we execute the default action, which is drop, right? So if we go back here, you can see that we activated this IPv4 exact. So this is IPv4 exact.apply. And you can see here we have IPv4 exact, it's being applied, but there's a miss. Why do we have a miss? Because we sent the packet to 20.00.1 and we don't have any entry in the table that we populated before, right? So there's nothing there for 20.00.1, specifically in the IPv4 exact. And now we have a miss. So what happens is, by default, as we know, there's a default action executed that is called drop. Now you might think, okay, so the packet is dropped. How are we going to continue? Well, the way P4 works is that it's going to be completing that block regardless of what if you drop or not, right? And again, this drop is simply setting a flag, and you can change it later on, right? So you might want to drop now, but then later on decide, no, I want to forward that packet. And this is why, okay, it's being executed, right? But then later on, we have another table, which is the LPM that is being activated. And if you go to the code, now we are here, the IPv4 LPM apply. So it's being applied, but now we have a hit. And we have a hit because we installed that entry at runtime, right, in the script that we executed before. We have a hit, and it will show you here the handle of that entry. So you know exactly which entry in your table was hit and it's matched, right? So we have a hit, then the forward action is executed. And there you're gonna be basically doing whatever commands you have in it, right? In our case, we modified the TTL, we did other stuff as well, right? Now in the logging here, we don't see those, but we know at least that it's being executed. Now the ingress is done. We start with the egress, we kept it empty, so there's nothing there. There's the deparser. Here we have the checksum update, so we did that, and that's because it's already written, but tomorrow we're gonna show how do we do that checksum update. And then we have the deparser. We emitted the IPv4 and the Ethernet headers, and the output port is 1, right? So what I want you to notice is that even though the drop was executed at some point, right? But because we executed another table that re-instructed the traffic manager, no, we need to send this packet out from a different port, then it really sent it. But if there was no other table that was modifying the egress spec, then the packet would be dropped. Okay, and when I was telling you about like the sequence of execution, this is what I'm meaning. Like when you have whatever you write here in the apply, this is how you need to read your P4 program. You start from top to bottom, right? First check for the validity of the header. Then we start by executing the tables and all the logic that we have. And we are verifying this by just looking at the logs to really describe what happened in the for the packet inside the switch. Okay. Now we're gonna send another packet, but this time for 30.1, and I will press a few enters here just to separate for the future logs that are gonna be displayed. So if I go to host H1 and use here send, but now 30.00.1, hello world. Okay, now we go back to the switch logs, and what we can see here again, the parser executed as usual. We start the ingress pipeline, right? The condition of the if statement is validated to true, so that's the if IPv4 is valid. And now we have a hit on the exact table, right? We have a hit, so we execute the forward and then we forward the packet. And notice that whenever we have a hit, right? So this whole condition is not gonna be activated, so we're not gonna execute the IPv4 LPM table. So we're just gonna be stopping there. Why is that happening? Because we specifically said that only if there's a miss in the exact, we then apply the LPM table, right? But because in the rules that we specified, we have a rule for that specific exact, so it's gonna be applying and then hitting, forwarding the packet, and we're not gonna reach this specific apply here for the LPM. Again, this is just how we wrote the program. It doesn't mean that's the only way. You can play with the tables, put one table after the other, see the behavior. You can have more interesting or more even complex arithmetic operations and assignments for the headers here. And you should be able to verify all of these. You want to have like further verification. Let's say you modified some headers here. You can look at the Wireshark traces and you'll be able to see some changes there as well. Okay, and basically that's it for lab number 6. If you have any question, just let us know.
Well, thank you, Lee. Thank you for the presentation.
Thank you.
I don't see any question. I see the hand of Shuju. Do you have any observation, question?
Sorry, I forgot to lower my hand.
No problem. So I will be posting. I noticed a message from Laura. Laura is one of the organizers. The video, the recording of yesterday should be already in the platform. When you log into the platform, you enter the room for this workshop. The video should be there. We will also be posting the recording in our website. So that should be there by the end of the day today. And the video of today will be by tomorrow. So before we finish, this will be the last activity of today morning. In the afternoon, we always have this office hours is for open discussions, or if there is anything you want us to discuss, that's office hours, but we will not be moving forward to the next topic. The next topic in our program will be a runtime controller, checksum, the parser. That will be everything discussed tomorrow. There are two question observations. So what would be the best practice to have multiple actions in the same table? I mean, we can do nested if statements and use the hit to match against the same table again and again. But is there other recommended ways of doing so? I will, Ali, Eli, Jose, you who are doing this lab, what would be your recommendation or observations to this question?
Well, what I would say is that, like, whenever you program in P4, it's correct that you can do these if statements and maybe have actions without their corresponding tables, and it's possible to do that. The best practice is, in my opinion, like when you do P4, it's about how match action table, the concept of match action table. You have a key, you match, and then you execute an action, right? While you can do in other ways, like having multiple if statements, it's best for readability and for also on the hardware. When you compile, the compiler will try to insert the resources, or will try to insert the table in the right stages and the resources. So there's a lot of compiler optimization happening there. If you write it using this match action, you minimize the if, you maybe just keep the if for few conditions there, that would be better. I have also to mention that when you write an action, so you can have a dangling action where you can specify whatever you want there, but in the and you can call it without its table, and that would work. The compiler will not complain. But what happens in the background is that the compiler will create a table, like a dummy table, basically, and give it a random name, and then will associate this action to the table. I don't know if that answered your question, Italo.
And Eli, what you have been working on this for quite a bit for the last couple of years. Also, something that we have noted at USC is that there are many things that you can do in BMB2, and BMB2 is great to develop ideas or to put in practice some initial ideas you might have. But in hardware, if the code is very complex, nested if, or it might not compile. I don't know if you want to talk about that, Eli. What is your experience with that?
Yeah, certainly. I mean, it's a good point. At the end, remember when we talk about the hardware, there's a limited number of stages, right? When you write a lot of if statements, you might think that, okay, this might be like the only way to do it. And sometimes if you have a lot of nested if, you're gonna run out of stages and the compiler will not compile your P4 code. But when you write more in, you know, kind of match action table style, the compiler is really smart in the sense that it tries to really use the resources. So it will, you will see, I mean, if you compile on the hardware, it's not like here you type P4C and it just works. It usually takes some time. It will take 30 seconds, sometimes up to 1 minute, because it really tries to optimize and find the right placement of these resources to fit them into the limited number of stages that you have. Right. And at the same time, it will try to make sure that it solves all the, kind of like any other compiler, to solve all the data dependencies and make sure that two tables, for example, if they are not related in any way, they place them in one stage. There are more things that you can do in that area. It's a little bit, it gets complicated, but also you can specify where to place, in which stage you want to place a certain table. And these are a little bit more advanced. And in the training of let's say, we're talking about Tofino, that's the hardware switch, you can get much more information about doing further optimization from yourself to make sure that your tables are being placed well. In BMV2, as Dr. Jorge was saying, it's a really good you know, software switch, but it's not a production switch. So it's just to test some ideas, but it rarely complains about the complexity of the code, right? it will keep compiling because it will assume that you have unlimited resources or the resources that you have on your PC, basically. In the hardware, it gets different. And you have to always keep in mind that you are writing those tables, you want to make sure that you minimize the dependencies, because the more dependencies you have, the more you are forced to place tables in different stages. And then you will end up, even if you are doing a very simple operation, you think that it's simple, but it's not really simple. It's going to be spanning over multiple stages, and then your program will not compile. So there is a lot to be considered whenever you write for the hardware. I would say mostly try to write your application in a way that is hardware friendly, I would say, because you can write let's say a Python or a C application. It works well. You can write different ways to get this to the same goal, right? They all work well, but in the hardware, you really need to find the right way that will force the parallelism to be executed in your hardware and minimize the dependencies. BMV2 is great for learning like we are doing now, but later on, you will start with the hardware, and I would say it's not like a super different. Like at the end, we are still using P4, right? The table definition is the same, the action, all these syntax is the same. But the tricky part is how to write an efficient code that will compile and be executed there.
Yeah, and Italo, by the way, we are developing some lab libraries that run on the real hardware, on the Tofino hardware. We can give access to those for to educational institutions. So if you are interested, just reach out to us, and you can have access to a library running on the real hardware. There is another observation of Vinicius. How do you recompute the header checksum when you modify certain fields?
Yeah, so you can see in the agenda, this is day 3. We're gonna go over that checksum recalculation. This is lab number 8, but it's really simple. There are some functions that are available as externs that you specify the checksum algorithm. For example, in IPv4, they use CRC16, the cyclic redundancy check algorithm. And basically, it will take a batch of input fields, which are the values of these fields in your IPv4 header, and then it will produce a new checksum value. You will override the previous one, right? And this way, whenever your packet receives the other end, it's not going to complain about an invalid checksum. But in short, there is some externs available with some hash algorithms that are commonly used for checksum calculation that are available for you, and even in the hardware.
Yes, and Vinicius, we will be going over that in detail tomorrow. So again, we finished day number 2. We will be here for office hours, general questions you may have. Tomorrow we will continue with our program, runtime controller, and then about checksum recomputation, packet deep parsing. And with that, we will be finishing the first part of the workshop. Then Thursday, Friday, we will be talking about stateful elements. So I will stop the recording here. We have, I will see some of you tomorrow if you don't come back for office hours today. If you decide to come back for office hours in about 1 hour, we will be here for any general discussion. Thank you, everyone. Have a good rest of the day. And this channel will stay open because we will be coming back here again in 1 hour. Eli, are you still there? Or Jose?
Excuse me, doctor, I didn't hear you.
Welcome back to the second day office hours. I'm sharing my screen right now and just summarizing what we did so far. So we, day number 1, intro to P4 and data planes and how to use the tools. And today what we did this morning is we learned how to write parsers and how to define the match action tables within the control blocks, and also how to write actions. We learn how to use exact matching within the tables and also along its prefix matching tables. And that's where we are. So at this point, really is up to us if we want to, from any of the attendees, want to cover any specifics about this or go over a lab. So what this morning we covered 2 labs, Parser Implementation and match action tables. We didn't do the match action tables part 1 because it was covered already in lab number 6. But is there anything that this was by Jose and Eli? Jose and Eli, is there anything that we did not cover that is worth mentioning here, on your opinion?
The only difference in that lab is that we apply an action in the apply block. We drop a packet, so we show also, but Eli explained that in lab 6 so that we can invoke actions in the apply block. We do that in lab 5. That's the only difference I found that could be relevant. And then it's just creating a table with exact match. And that's it.
Okay. So basically then we cover everything in lab 6 and Eli described that, what you just said.
That's correct.
So from lab 4, 5, and 6, it's anything would you, or even from lab 1 through 6 so far, Eli and Jose, anything that is worth mentioning that could be important before going into the more advanced topics tomorrow, Wednesday?
There is one thing that I think we can like clarify a little bit more. If you open Dr. Jorge, the slides related to lab 4, the parser, there is one.
Eli, do you want to open those
yeah,
slides?
Sure, I will. Just a second. So basically, when we define the headers, Min Ali explained all of this and he showed like during the code how to do them. I think it's also worth mentioning that sometimes if you're not planning to use some of the fields, you can compress them and put them in a single, let's say, name. So for example, here, you know, you have the first 4 bits for the version, which are translated here, and then you have the next 4 bits for the IHL. But if you look at closely what is happening here, you have from 8 to 15, right? And so basically these are the diff serve. But what you can see is the first 7 bits are the CP, for the differentiated services, and also the ECN, the explicit congestion notification. But if we don't, let's say we are writing a program and we're not planning to really use exactly the ECN field or the SCP, there is no problem in combining them and putting them into one field. And in fact, let's say here we are not using the version, or we are not using the IHL in any of our programs. So we can have a bit 8 and put them. And I'm not saying like it's a good practice to do, but I'm just saying that from a P4 perspective, it's like a tape machine in the sense that it has a head and it's reading bit by bit, right? So for it, if you put these as 8 bits, this is going to be the same output is going to be. So if you try to access the source address, you're still accessing the source address later on. Yeah, the other one, Ali, I already mentioned, which is to be byte aligned. That's also a very good observation, I think.
Thank you, Lee. Yes, it doesn't, what you just said doesn't mean that if you don't separate the SCP and ECN, you cannot access. You will just have to do it manually later on in your code. But if you don't use it, well understood, you just can combine.
Yeah, and in fact, I mean, this is, let's say, 16-bit, the total length, and the first are 16. You can put them in 32, and the P4 program will still have the same behavior. Nothing will change. And this shows how, like, really the P4 switch is not understanding what you are writing here. It just knows that this is this much bits. This field, let's say it's n bits. This is 4. This is 8. So it's all about the count of bits that is important here, and the order of these is important, right? So when you put the source address at the destination at the end, it means that to be able to reach them, you have to have this parser, which is like a tape. It has to read the first few bytes before, so that it reaches that value.
Okay. Yeah. Now, is there anything else? I mean, maybe that we just went too fast this morning that is worth anything that any of you think is worth discussing?
We also have a related lab to lab 4, which is header stack, where we do more advanced parsing. If someone is interested on doing that lab, it's already there in the other library. And yeah, is lab number 6. And that's interesting because we are dealing with a packet that has a variable length header. So that's interesting, how to parse and how to extract all the information.
And like also one thing, I don't know if we covered that, is same as like the tables and the sizes of the table is like it's based on the resources of the switch. Also, the parsing is limited to the resources available in the switch. So, for example, in our scenario, we're just like putting 2-3 states, which was simple and can be easily done in P4. But if you want to do more complex and a lot of custom headers, then you might reach a point where the compiler will basically complain or throw an error because like you've passed the parsing capability of the hardware resources. But that's like if you're adding a lot of states and transitions.
All right. Thank you. Yeah, regarding Jose brought the point of the other library, the more advanced library. We're just covering intro to P4 with BMB2 so far. And we will be starting covering the second library on Thursday. So on Thursday, we will go through more advanced topics. And I don't know, Jose, you said you mentioned lab number 6, I believe, in this second library,
Yeah.
header stack. I
Mhm.
don't know if you need to use any stateful element to keep track of the stack of headers.
No, we don't use a stateful element, but we show how to use the metadata in kind to do to store some values, which is not a stateful element but we do something similar with that with the metadata, the custom metadata, the one that you define.
Okay. Okay, so probably it's just better. I mean, it's a good example of lab, but it's better to is that lab introducing the learner metadata, something that can be done, like jumping from what we learned today to this lab number 6 in the second library?
That lab is a bit advanced, and for someone who is starting, I think it's better to start with lab number 5 and then lab number 6. Otherwise, it could be confusing.
Okay, all right. So I don't see any observation or question at this moment. So what we will do, I cannot share my screen because I'm not a host. So could you, or actually I can get back now. So there is no question. So what we will do is, let me just go to our website. We're done for today, and through lab 6, I recommend to do the labs all the way to lab 6. And tomorrow we will start our discussion with the runtime controller. And I think we will finish tomorrow this first lab library. That's it. I don't know if there is anything else to discuss. I think we didn't leave anything, Eli and Jose, I mean, without discussing. At least all the topics that we cover has been discussed.
Yeah, I think the session today was positive, and the attendees brought very good questions, such as tables without keys. We cover that. We will see that tomorrow in lab number 5, how to use a table without a key. That always we will execute an action, which will be the default action. That's a very good point. And yeah, I think this recording and all the materials that we develop will be very insightful for someone who want to start with before.
Yeah, and one suggestion is doing the lab. I mean, we got a really good question this afternoon, this morning, because some of the attendees were doing the labs and found some challenges. So feel free to bring those challenges tomorrow morning, and we'll be addressing them. So I don't see any question, any last comment. So then we will conclude for today, day number 2. We will try to upload, Jose and Eli, could you please, if you have access to the videos, to upload to our website as well?
Sure.
They will be there. I am already processing them.
Okay, thank you. The videos will be in our workshop website here. And we're meeting again tomorrow, 9 a.m. Pacific time. So have a good evening, everyone, and we will talk tomorrow.
Thank you.